Okay, here's a new example to take a look at. We're going to do this one a little quick to give you an overview, and then we're going to dive back in and take these problems much slower and break it down piece by piece a little bit smaller. If you've gone through the PowerPoint already, you've already seen that there's a bunch of equations we're working with. And how does that all come into play? Well, the first thing is, got to size up your recharge basin. That is, can't use yellow, I can't read that. That is Q is equal to CIA. Same thing we've been doing all along. So our storage volume for the basin will be 0.3. That's a composite value that we typically use for subdivisions. In this case, we're multiplying it by 8 inches over 12 inches per foot times a 10-acre site. 10 acres times 43,560 square feet per acre. So we need to store 0.3 times 8 divided by 12 times 43560 times 10, 87120 cubic feet. Let me just double check that number. 0.3 times 8 over 12 times 43560 times 10. Yes, okay, so small recharge basin, 87,000 cubic feet of water to be captured. So that's our, just called 87,000. That's the volume of that recharge basin. We'll go into sizing those up later, but we just at least need to know what the capacity is. Now, the biggest part of recharge basins is how much water goes into the pipe and how do we work that all out? Well, what I have here is I've kind of outlined some storm drainage areas. Okay, and storm drainage areas are how much water goes to each of the different systems. So in this case, we have storm drainage area 1 and 2, 3, and 4. These are called SDAs, storm drainage area. Storm drainage area, storm drainage area. And I figured this out by looking at a topo map and seeing how much water will work its way and get into each of these catch basins. Okay, so some will be on the road, some will be from other areas. For example, let's look at storm drainage area 1. And these numbers are not off any specific map, I'm just kind of throwing them out there. The amount of water going into this is also figured out by Q is equal to CIA. But here's the difference. This is not the same Q equals CIA as you see at the first part of the problem. And that blows people away because we're using the exact same variables, the letters, but they mean something totally different. I wish it wasn't the case. That's the way it works. I can't do anything about that. So Q is equal to your flow rate, which means it is in cubic feet per second. It's how fast the water travels, okay, the volume per second. I is your intensity. Before it was in feet, now we do it in terms of inches per hour. And your A is your area, but it's no longer in square feet. Now it's in acres. Oh boy. Okay, so Q is equal to CIA, and let's look at the units now. That will be equal to, C's unitless, so we get an inch per hour times an acre. And I'm telling you that's equal to cubic feet per second. So these units have to be made into cubic feet per second. That's what we're tasked with. So how do we go about doing that? Hopefully some of you are already thinking, well, I know my conversion factors, I can work with that pretty easily. I want to make it even simpler for you. It's magic. Okay, let's just do a quick example off to the side. And that's kind of thick. There we go. Let's say I give you, if you're given an area equal to 1 acre, an intensity equal to 1 inch per hour, and a runoff coefficient equal to 1.0. If I gave you that, what's Q going to be equal to? Let's go through this whole process. Q is equal to CIA. So Q is equal to C, and I want to have this in cubic feet per second. Remember that because we're going to change all of our units as we go through this. So 1.0, that's unitless, times the intensity. Intensity is 1 inch per hour. So I need to get feet and seconds out of that. So what I'm going to do is I'm going to multiply this by 1 hour over 60 minutes times 1 minute over 60 seconds. And that I'll show the cancellation in a second. But I need to get my inches into feet. So I'm going to multiply that by 1 foot over 12 inches. That's the conversion for intensity. Then I'm going to multiply by 1 acre times 43,560 square feet per acre. Let's take a look at the cancellations, make sure I did this right. Hour and hour, minutes and minutes, inches and inches, acres and acres. And what I'll be left with is feet, square feet, and seconds. Looks good. I think it looks good. So what's Q equal to? Pause this for a second. You do the math. I already know the answer to this. I want you to work it out and tell me what you get. So pause this for a minute and figure it out. Okay, welcome back. So I got an answer of 1.008 cubic feet per second. Great, you got the number. What does that mean? What did that just, what was all that about? What did it tell us? Well, it turns out that if you use acres and inches per hour, the numbers all magically cancel out. We're only off by 0.008 of a cubic foot. So you're going to be off by about a coffee cup worth of water per second going through a drainage pipe. Not a big deal at all. You always have the option of going through this entire conversion. You can always do that. Or you can take Q is equal to CIA, where C is 1.0 times 1 inch per hour times 1 acre, and then magically it's 1 cubic foot per second. I would go with that. That's a much better way of doing it. It's also the industry standard. In industry, we work with cubic feet per second coming out of an inch per hour and an acre, and that small amount of water that's lost through the rounding differences, it's not a big deal because this C value, that's a guess. It's an estimate. Guessing sounds like we don't know what we're doing. It's an estimate, but it's not perfect. So let's go back to this example real quick, where if we take a look at storm drainage area 1, throw some numbers in there. If we take storm area 1, let's say that, what just happened there? Uh-oh. There we go. Okay. I need to give you a runoff coefficient. That's 0.3 for the area. The intensity stays at 8 inches per hour. Okay, we're going to edit this out. So we're going to get Q is equal to CIA for the storm drainage area. C is going to be equal to 0.3. A is going to be the areas, the acreage of that. So let's just say that the acreage of storm drainage area 1, if we had to split in quarters, let's maybe make this like a 2-acre site. That's 2 acres. That could be 2 acres. And these might be 3 acres and 3 acres. So we have 2 acres. And then what's my intensity? Okay. If you just said 8 inches per hour, you're incorrect. You're thinking correctly, but as with everything we're showing you today, there's something different we're doing with the intensities now. Now what we're going to look at is how much water can get into this basin. How much water gets in there at any one given time. And that is one more equation of 120 over T plus 20. So if you haven't turned it off already, you're probably shaking your head saying, what's all this about? It's another equation we have to work with. T is your time of concentration. Okay, before we get into this, take a quick break, get up, walk around, stretch your legs, get some oxygen in your brain. We're going to come back, we're going to look at what the time of concentration is, and then we can actually start putting all these parts and pieces together to it. Trust me, in the end, it'll be good. Getting through there, getting the basics down is a little bit tough, but once we get through this, you'll see it's not quite as bad as it seems right now. All right, so go take a break, come back, let's look at the next part of this. So to calculate time of concentration, it's not something we actually do through equations. What we use is a nomograph. And nomographs are something that you may probably have never seen them before, but they are such a very, very useful and handy tool in doing calculations pretty rapidly. They have these for a lot of physics problems as well. Basically, it's a graphical solution to an equation. And what this nomograph that I have here, and there's also a copy of this saved onto Blackboard for you, printed out as many times as you need. Basically, what you do is you draw straight lines and get your answer, or approximate your answer. And what this takes into account is quite a few different things. So first of all, you have to know what the length of the strip of land is that you're starting with. So that's how far it's going to be to get from the furthest point away on the storm drainage area into the catch basin. Then you have to know exactly what type of ground surface you're going through. Is it going through something that's paved, where the water moves very fast, or is it going through very dense grass where the water is going to be moving much slower? And there's all areas in between. You as the designer get to choose where that surface falls, where that number falls. It's not a perfect science, it's an estimate. So you can, there's definitely some tolerances on what the numbers are going to be. The way we're going to do it in this class is I'll give you very specific information, like solve it for bare soil or solve it for an average grass surface. This way our numbers come out pretty close together. Then we have what's called a pivot line. So we draw a straight line, we hit this line, and then we use that as a pivot point to go through the percent slope of what the land surface is. Again, you have to go back to your topo map and figure out what the elevation is at the bottom where the catch basin is located, and the elevation where that water originated from. And the difference in elevation divided by the length of that land strip that it traveled, that will give you your average percent slope. So let's do a quick example on this. Let's say that we have the length equal to 500 feet. We're going through bare soil, and we're going to have a slope equal to 1%. Find what your time of concentration is. So for this, you're going to need a straight edge. I'll show you on this one. You can print it out later on and try them on your own. But I'm going to start out, hope this works, 500 feet. I'm going to take that through bare soil. There we go. Oh, that shifted. So you'll notice that it goes from the 500 feet through the bare soil line, and that gives us a pivot point, okay? These numbers on the backside are based on rational C values, where bare soil has a rough estimate of a C value of about between 0.4 and 0.5. We could do it by that method as well, but to be honest with you, 99% of the time you're working with the left side of that column. So then from that pivot point, we then, oh, I gotta go to the line. We then go from that pivot point through, we say 1% slope. There's my 1% slope here. I got to extend it that way. I just draw a line right on there. And that is my time of concentration right there. That will be 15, 16, 17 minutes. 17 minutes. That would give me an intensity of 120 over T plus 20, which is 120 over 37, or 3.24 inches per hour. That's how you find your time of concentration. It's all done through nomographs. And depending, again, the strip of land, the ground surface you're going through, and the percent slope. You can run into trouble where if you wind up having slopes that are exceeding 20% or less than 0.5%, it's very hard. You have to basically estimate where that's occurring at. And if you wind up getting times of concentration less than 6 or more than 35, you're going to run into some trouble. As you get further into drainage design, some municipalities give you a minimum time of concentration that you have to meet, which means if you're less than that, more than that, nope, less than that, you have to increase it to get to a certain point. All right, we'll come back and do more time of concentration problems. I want to just take this time of concentration idea and bring it back to that last problem we were on to just kind of finish out that storm drainage area. So through the magic of video editing, we're back where we were before. And we just figured out that T was equal to 17 minutes for this example, right, for the storm drainage area 1. So in this case, intensity would be 120 over 17 plus 20, or 120 over 37. We said that's 3.24 inches. So what that's going to give us is the Q of the water going into the pipe. Q is equal to CIA. So Q will be equal to our runoff coefficient of 0.3 times the intensity of 3.24 inches per hour times 2 acres. And again, we don't need to do any conversions on that. 0.3 times 3.24 times 2, that means the Q is 1.94 CFS. So what we need to do is we need to design a pipe that can handle 1.94 cubic feet per second flow going through there. So that'll be the next thing we jump into, is how we figure out what that flow rate is. Flow rates. There's two problems, or two numbers we have to, two equations we're dealing with for flow rates. The first one, Q is equal to AV, and the second one is the Manning equation, 1.486 R to the 2/3 S to the 1/2 over N. So what do these equations work for us, or what do they do with us? We're going to see some variables that kind of change shape once again, such as area. That's now area of a pipe. This Q is the Q we calculated before, is cubic feet per second. And now we have velocity of water. Slope we saw before was in percent grade. Now slope's going to be in feet per foot. So we got to be very careful with the units on everything because it does make a big difference in the problem. So let's talk about this equation first. Q is equal to AV. This is important because water is an incompressible fluid, which means no matter how much pressure you put on that water, you cannot make it any more dense than it already is. It's in its most dense state. Yes, I know when water freezes, we have a bit of a change there, but don't worry about that. If water's frozen, the pipes aren't working, so it's kind of a non-issue. Let me give you an example of this. Because water is non-compressible, if you change the area of a pipe or you restrict a pipe, you cause that water to move faster. And if you make the pipe larger, it winds up moving slower. An example of this is taking your garden hose. Go outside, turn on your garden hose, and watch the water stream out the end of the hose. If you put your thumb over the end of it, you're restricting it. You're closing down the cross-sectional area of the end of the pipe. And what happens is the water now moves out faster and it goes further. The faster it moves, the more energy it has, the longer the distance it's going to shoot out. That's a perfect example of what's happening. When we deal with stormwater runoff, if you make the pipes really small, the water flies through really quick, which is not a good thing. If you make the pipes too big, then the water moves too slowly, and that's not a good thing either. We want to keep the velocity somewhere between 2 feet per second, greater than or equal to 2 feet per second, and 8 feet per second. Now, some municipalities have been going as high as 10 FPS. You'll see some out there that do that. If you're allowed to do it, go for it. I would just say try and keep around 8 feet per second. We're going to kind of keep that as our number during these calculations. So that's for the water in the pipe. Depending on what the cross-sectional area of the pipe is, that will give us a certain flow rate of water. So that's some things to keep in mind. Then we have this other equation, Manning's equation, 1.486 r to the 2/3, s to the 1/2 over n. So in the PowerPoint, I gave you all the variables that we had for this. V is your velocity in feet per second. R is your hydraulic radius. That has units of feet. S is your slope, and that is in feet per foot. And then N is your roughness coefficient, and that's unitless. This 1.486, that takes into account the effects of gravity pulling water and the weight of water being pulled through a pipe and how that changes things over. So what we can do is if we adjust the slope of the pipe, we can make the water move faster or slower. Make the pipe flat, water moves slow. Make the pipe pitched steeper, the water is going to move fast. So that changes our velocity. And if we change the velocity, then we also change our flow rate. So that's all through slope. Let's talk about this hydraulic radius. Okay, there's a little video I have in there that explains what hydraulic radius is as a visual, but let me give you my best explanation of doing so. When we have a pipe, okay, one of the important things with this is we have to design this with the idea that the pipe is flowing 100% completely full with water. Because if the pipe is not filled completely with water, all the stuff I'm telling you right now goes right out the window. And we don't want to do that. There's a catch to this. How often does the pipe flow completely full? Almost never. So why are we doing this? If this is the method we go through, this is for the worst case scenario. So when we do get that gigantic rainstorm, these pipes don't back up and cause serious problems. There'll be a video a little bit later I want you to watch. I'm actually going to put it into today's lesson because it's kind of a sort of a funny video of what happens when these pipes are not sized correctly. It's amazing the energy behind some of these pipes. So that'll be the last thing we do for the day is check out that last video. But this hydraulic radius, that's equal to the area divided by the wetted perimeter. And the wetted perimeter is nothing more than what's the area that's actually touching the outside of the pipe and getting wet. So it's that. And that's your, what happened to that? Well, pretend that blue is still there. That's your circumference. I give up. All right. So for circular pipe, what's the area of a pipe? Pi? No, not r squared. Remember, we're dealing with diameters. So pi d squared over 4. And how do you get the circumference of a pipe? No, not 2 pi r. It is, outsmarted myself, pi d. Pi times diameter. Pi times diameter. Okay. So what's going to happen is we're going to get some cancellation here. Pi and pi cancels. Diameter and 1 diameter cancels. And we're left with d over 4. So our hydraulic radius is d over 4. Only for circular pipe. It only works this way for circular pipe. As long as you put your diameter in feet, your hydraulic radius shows up in feet as well. We're going to go through pipe diameters as well today. Unfortunately, we always specify pipe diameters in terms of inches. Like if you went to Home Depot and you tried looking for a 1/2 foot diameter pipe, it's not going to show up, but you can find 6-inch pipe. Or if you want to find a 0.25 foot diameter pipe, you need a 3-inch diameter pipe. So we speak in terms of inches, but we calculate in terms of feet. So good thing for us, we're only dealing with circular pipe this semester, but I do want to make you aware that they also make square pipe. They make elliptical pipe, which is really some cool stuff. Very, very useful pipe. It's expensive, really expensive, but very cool stuff. And this also works for trapezoidal sections. Okay, so where would you ever see a trapezoidal pipe? Well, if you've ever watched any action movie where there's a car race running down through Los Angeles and you see them running underneath the bridges and these big trapezoidal concrete pathways, that's a drainage system. Okay, it's during the dry period. But the Manning equation, this 1.486 r to the 2/3 s to the 1/2 over n, this works for anything in the world. If you want to figure out the flow rate of a river, as long as you can calculate what the wetted perimeter of that river bottom is, and you can figure out what the area is, hydraulic radius is area over wetted perimeter. If you can figure out those two things, you can calculate a hydraulic radius. For our class, we're just going to deal with circular pipe though. Okay, d over 4 is all we have to work with.